My favorite student, good old... Whoop! Wow, that finally started moving. I was kind of wondering. Let's try that again, Mr. Dueck. I like number one, I like number one, I like number one, I like number one. Somewhere on your test, I'm going to give you 2 point charges and how far apart they are. If it's multiple choice, I may be really nasty and not put them in a nice straight line with each other where you got to pull out some trig. Written, it'll be in a nice straight line. If they're not in a nice straight line, then probably it's a scalar question and you don't need to worry about it. Little hint. So first of all, find the magnitude of the electric force. Okay. My abbreviation for electric force, just like I do gravity, F with a little g, I do electric force, F with a little e. And that's going to be K, Q1, Q2 over R squared. I can also find the force by going QE if I know the electric field, but I don't know the electric field, so the meh. It's going to be 9 times 10 to the 9th. The left-hand charge is 5 times 10 to the negative 6. Mr. Dueck, that should be negative. No. We don't put signs in for forces and fields. The vectors, hey, here's another one for those of you that speak German. For vectors, the signs are verboten. Although verboten is probably spelt with a W, so that probably doesn't quite, I don't know. Anyways, verboten means forbidden. No? Is it over your head? Okay. The second charge, 3 microcoulombs. The 2 most common prefixes that I'll be using this unit are microcoulombs and millicoulombs. Over, careful. 2.35 meters, is that right? Yeah? Now it's plug and chug. I probably won't give you one quite this easy on the written. I would have no problem putting a third charge here and saying, find the net force on that charge, in which case you'd find the force between the 2 left-hand charges, you'd find the force between the 2 right-hand charges, magnitude and direction, and you'd add or subtract them vectorially. That would be a good written question on your test for forces. This is a little too plug and chuggish. So I said I like number 1. I really like number 1, B, and C much more. 9 times 10 to the 9th. 5 times 10 to the negative 6, 3 times 10 to the negative 6 divided by 2.35 squared. Did I type this right? Yes, 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 yes. Do you get an electric force of 0.024, 2.4 times 10 to the negative 2? Direction, it didn't ask for it, but by the way, direction, attract or repel? Attract. Usually what I'll do is I'll tell you one of the points is a fixed point. That means it's not allowed to move, and that way you're looking at the other point and you can say, oh, is it moving to the left or moving to the right? Right? Find the electric field, magnitude, and direction. I like B, definitely. So what I'm going to do is I'm going to find the electric field from point 1, which is K Q1 over R1 squared. I'm going to find the electric field from point 2, which is going to be K Q2 over R2 squared. And then I'm going to add them vectorially. The electric field from charge 1 is 9 times 10 to the 9th, 5 microcoulombs, 1.5 squared. Nine times 10 to the 9th, 5 microcoulombs, 1.5 squared. Works out evenly, kind of nice. I have an electric field of 20,000, I need a direction. So electric field number 1 is 20,000 newtons per coulomb. Which way would a positive charge right there want to move if it could because of charge 1? It would be attracted. Left. Yes? Repeat for charge 2. Electric field for charge 2. I'm not going to show my numbers here because I'm running out of room. It's going to be 9 times 10 to the 9th. Instead of 5 microcoulombs, it's 3 microcoulombs. And instead of 1.5, it's 0.85 squared. I get an electric field of 37,370. What was it? 37,370 newtons per coulomb. Direction, which way would a positive right there want to move if it could because of charge 2? Hey, also to the left. So final answer is going to be 57,400 newtons per coulomb left. That gets you 2 out of 2. Is that right? Yes? Okay. In terms of part marks, I would probably go something like this. Half mark for that magnitude, half mark for that magnitude, half mark for the magnitude, and a half mark for the direction. Something like that. C says, find the electric potential at location A. Curtis, by far, the most common mistake I see kids do this. That's not electric potential. What is that? But energy, electric potential, energy. So Nate, if you did that, be sheepish and foolish and say, no, 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 no. Electric potential is another word for what? Voltage. I'm going to find the voltage from charge 1. I'm going to find the voltage from charge 2. And then I'm just going to add them up. And they're scalars. No vector math. The voltage from charge 1 is KQ1 over R1. It's going to be 9 times 10 to the 9th, 5 times 10 to the negative 6. No, Mr. Dueck, you're doing a scalar. You better include the sign. Negative 5 times 10 to the negative 6. I get a voltage from charge 1 negative 5, 1.5, delete the squared. Is that right? 9, yep. Of negative 30,000 volts. Direction doesn't have any. It's a scalar. I'm going to get a voltage from charge 2 of KQ2 over R2, 9 times 10 to the 9th, positive 3 times 10 to the negative 6, all over 0.85. Delete 3.85. I get a voltage of positive 31,764.7. And I add them up. Plus negative 30,000. Yeah, I could have done it in my head. I get, you know what the voltage at location A is? 1,760 volts. That's the location. That's the voltage at location A. Okay? 2 marks for that. Half mark for the negative 30,000, half mark for the 31,700, I don't know, and then 1 mark for the answer, something like that. Turn the page. How much work? Number 2 says, how much work? Sadly, I can't use force times distance because between point charges, in fact, you know what? I'm going to draw a little picture up here. Here's Q1, which is negative 8 microcoulombs, and it looks like we're moving an electron from, here's my initial, and I guess we're moving it in close. Does it want to move towards the negative? So will it take work? Yeah, I'm going to have to push. So I should get a positive answer Okay. And our final distance, our final location is going to be 0.15 meters. Okay, work. Change in potential. I think we're starting and ending at rest. This is going to be final minus initial. Where are we starting? How far away? Yeah. So my initial is 0. You know what? This is going to be really yucky, but this has turned out not to be so bad. So the work is just going to be the potential energy final, which is K Q1 Q2 over R final, which is 9 times 10 to the 9th. Q1 negative 8 times 10 to the negative 6. Q2 negative, it's an electron, 1.6 times 10 to the negative 19. All over R final, 0.15. You'll notice I get a negative times a negative. Manish, I get a positive answer because it will take work. Doesn't want to go that way. It's like lifting something up off the ground. I get, no idea, 9 times 10 to the 9th, negative 8, negative 1.6 times 10 to the negative 19 divided by 0.15. Do you all get that much? No? Yes? 7.68 times 10 to the negative 14 joules? Not very much work. You're moving an electron. It's not a big charge. Okay. In terms of part marks, I would probably go 1 mark for that, 1 mark for that, 1 mark for the numbers, and 1 mark for the answers. Oh, something like that. Now, the other thing I could do is I could reverse this question. Instead of starting at infinity and moving it in towards the negative, I could start at location final, and if I let it go, which way does it want to move? Which way does it want to fall? Up, to the right. It would speed up, much like question 3. A proton, initially at rest, will have what speed at point y? Is there a change in height? Is there a change in speed? This is a job for conservation of energy. Starting at rest. I want to find the final speed. Really, I want to get that by itself. So I'm going to say it looks like it's going to be PE initial minus PE final. That equals KE final. I think it's going to be K Q1 Q2 over R initial minus K Q1 Q2 over R final. That equals a half M V final squared. How much room have I got? Oh, good, a fair bit. It's going to be 9 times 10 to the 9th. Q1, 5.5, positive. Q2, it's a proton. All over R initial, 1, minus ditto mark, ditto mark, ditto mark, all over. We did this with gravity too, didn't we? R final, not 2.5. 3.5 from the original point. That equals a half mv final squared. I'm going to crunch the left side. 9 times 10 to the 9th, 5.5 microcoulombs, 1.6 divided by 1. You didn't need to divide by 1. I know, I just want to set up the template so that it works when I go backspace. I get 7.92 times, so I get 7.92 times 10 to the negative 15 minus, same thing, but with a 3.5 here, 2.263 times 10 to the negative 2.263 times 10 to the negative 15. That equals a half mv final squared. Please tell me I got more room. Oh, I basically don't. Okay, this is going to be yucky. I got to move over here. 7.92 minus that. Okay, I got 5.657 times 5.657 times 10 to the negative 15. That equals a half mv final squared. So v final, sheesh, it's going to be 2 times 5.657 times 10 to the negative 15 divided by the mass. Which mass? What mass is moving? What charge is moving? Oh, that's on my formula sheet. I don't have it memorized. What is the mass of a proton? I know it's not 1.67, but I can't remember more than the to negative 27? And here's hoping we're not going faster than light and violating the universe. Let's find out. So that answer times 2 divided by 1.67 times 10 to the negative 27 square root of that whole thing. Do you get 2.6 times 10 to the 1, 2, 3, 4, 5, 6? Yep. Woohoo! If you got that, you get 4 out of 4. Otherwise, here's how I gave out part marks in the past. So in the past, it looks like I gave you 1 mark if I saw conservation of energy, 1 mark if you got the KE by itself, 1 mark if somewhere I saw that 5.657 times 10 to the negative 15, and then honestly, this should be worth 7 marks, and this is what it would be worth on the written section, and I could give out more part marks, because this is kind of a dumb way to give out part marks, but there you go. Can you give yourself a nice, oh, and there's part marks, by the way, for the last one. Can you give yourself a nice clear score out of, count 'em, 14, please? Okay, let's continue. I called this parallel plate force problem. So recall from last lesson, we said if you take 2 parallel plates that are fairly long, and by fairly long I said on the atomic scale, this is fairly, 5 centimeters, 10 centimeters, plenty long enough on the atomic scale. And you make them out of some metal, copper, aluminum, whatever, and then you set them parallel to each other and you charge the top one positively by removing electrons from it. And you either hook the bottom one up to the ground to make it a charge of 0, or you can force electrons. You get a uniform electric field. And that electric field can be calculated by taking the difference between the voltage divided by how far apart the plates are in meters. If we were to draw the electric field, it would look like this. First of all, in between those plates, which way does the electric field point? Up, down, left, or right? If you put a positive in between those plates, which way would it want to move if it could? Okay, so the electric field would look like this. To show that it's uniform, what we would do is we would draw lines exactly the same distance apart. Because remember when I did electric field diagrams with you from point charges earlier this unit, those are supposed to be exactly the same distance apart, and they're not quite because I can't draw. Let's do that one a little bit further over. That's a uniform electric field. If you did this, that would be wrong because you'd be saying somehow right there the field was stronger because the lines are closer together right there. Now, this isn't perfect. At the ends, the electric field curves a little bit. This is why televisions never quite had perfect images or perfect screen. There is some noise. But in the middle there, you have a lovely uniform electric field. On the big review, it gives you several different questions on the multiple choice where they show you pictures, drawings of electric fields between parallel plates, and they'll say which one's right or which one's wrong. Look at the direction and then look at the uniformity of the lines. Okay. Example 1 says, explain why an atom will be ionized. Explain why an electron will be ripped off of an atom if you place it in a sufficiently large electric field. So we have a negative electron. Let's actually put that negative electron right there. Okay. What are the forces acting on that electron? Normally I'd say get the obvious one, but I think with the mass of an electron, gravity is pretty negligible. What's keeping it near the nucleus? What's the charge on the nucleus? Positive. So there is a force of attraction. What direction is the electric field in my diagram here? So that's which way a positive would want to move if it could. Which way would a negative want to move if it could then? Think about it. If a positive wants to move to the right, which way would a negative electron want to move? Okay, this electron is feeling some force this way, but it's feeling a huge force to the left. And if we make that electric field really, 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 really big, because remember we said that force was equal to charge times electric field. So if the charge is the electron, but if I bump up that electric field, I can set it up so that this force here is bigger than the positive attraction force. I will have ionized this atom. I will have ripped loose an electron. Okay? So if electric field is large enough, it can rip loose an electron. The electron wants to stay close to that positive nucleus, but we can apply a bigger force pulling it away. Just remember though, Claire, the force will be in the opposite direction of the electric field, because we defined electric field as which way a positive would want to move, and electrons are negative. Okay? If we're talking about air, mostly nitrogen and oxygen, it turns out that an electric field of about 3 million newtons per coulomb, or about 3 million volts per meter, that's enough to start ripping electrons off of air. That's what you're hearing on a staticky day when you hear the crackle noise. You're actually ionizing electrons. You generated a big enough electric field over a very, very small distance to do it. So this may seem like a lot, but the crackle that we hear when we pull apart clothes that come out of the clothes dryer, you're actually ionizing the air. You have an electric field of more than 3 million newtons per meter. Thank you. The shock you get when you walk across the carpet on a cold day, as your finger approaches the metal doorknob, all of a sudden when you reduce the distance, because remember, so one way of making the electric field bigger or not need to be is to reduce the distance. All of a sudden you'll have enough for the electrons to jump to the door to spark. What they're doing is they're ionizing the air between the door and your finger. You get a shock. And lightning. Each of these effects is accompanied by light. The reason there's light, a spark, is because what happens is this electron, when it gets bumped to the next atom over, is in a higher electron shell that it wants to be, and it wants to fall back down to its proper electron shell. But in order to do that, it has to get rid of some energy. What form does the energy that it gets rid of take? Begins with the letter L and rhymes with ite. It gives off a photon of light. That's all a spark is. That's what's going on in those little light things. Okay? Your fluorescent lights on a much more industrial scale. So, we can think of a cloud, as long as it's reasonably flat, as long as it's not a really, really huge bushy cloud, we can think of it as roughly a parallel plate to the Earth. I know the Earth curves a little bit, but not that much over a kilometer. So if we had a cloud that was a kilometer long and fairly flat along the bottom, and the Earth is a kilometer long, we can essentially say we have a situation like this. Now, as cosmic rays come through the cloud, they can actually knock off electrons. They can actually separate charge in the cloud itself so that you can end up with the bottom of the cloud being negatively charged, or the bottom of the cloud being positively charged. In this case, positively charged. How close does the cloud need to be for a lightning bolt to occur? The air breaks down at about 3 million volts per meter. Okay, so we know that electric field is the voltage divided by the distance. What's this question asking me to find? Distance. Oh, let's get the D by itself. I think the distance is going to be the voltage divided by the electric field because stuff moves diagonally. If the cloud manages to create enough voltage due to cosmic rays so that you have 2.5 times 10 to the 8th volts, and we know that the air breaks down at 3 million, and I'm pretty sure 3 million is 10 to the 6th. How close does this cloud need to be to the ground before lightning will jump? You get 83.3 meters, okay? What if, using these made-up numbers, the 3 million is an accurate number. The voltage generated, well, that varies depending on the storm conditions. You can get on a very, very muggy, stormy day where the clouds are moving a lot, they actually are sort of rubbing against each other. You can generate lots of electric friction and separate charges and get a bigger voltage than that, or you might get a smaller voltage than that. Smaller voltage, the cloud would need to be closer. Bigger voltage, the cloud could be further away and still jump. So let's do a thought experiment. Suppose the cloud was 84 meters away. Could it jump to the ground? If it was 84 meters away. It's meant to be obvious. Could it jump to the ground? Could a lightning bolt jump to the ground? William? No. So, where would it jump to? Hey, how tall are you guys? About 1.5 meters? Oh, are you saying that you as a human being, roughly when you're standing upright, resemble a tree or a lightning rod, and you might be enough to close that little bit of distance and have it arc? This is why humans get struck by lightning. You're essentially a not very good conducting lightning bolt. Okay. Or, example 3, where don't you want to be in a lightning storm? You don't want to be there. If you're ever hiking in the mountains on a stormy day, being very serious, no joke, and you start to feel the hair on the ends of your arms stand up, get out of there. Tell your friends, overrule anything you're doing. Say, we need to go either to shelter or we need to get to a lower altitude. What that's saying is the electric field has built up enough to cause the hairs on your skin to repel each other. You're really close to being the lightning rod. Get out of there. Okay? Or trees, this is why you don't stand underneath a tree. That's bad. Even if you're standing there, what happens is the lightning could go here and then arc into you or travel through you. Boats are bad, especially a certain type of boat. What are the worst types of boats to be in a lightning storm? Sailboat. Why sailboats? And what are the masts almost always made out of? Yeah, they're essentially lightning. There are reams of controversial literature as to what you should do in a sailboat if you're stuck in a lightning storm. Some people advocate clamping jumper cables to the mast and then trailing the jumper cables in the water. I don't think those jumper cables will provide a sufficient ground. I think they would get fried and you're still going to get shocked. Really, we don't get lightning storms on the West Coast the way they do down in Florida. But any sailors in Florida, they'll tell you every half hour you're looking on the horizon, and if you see storm clouds on the horizon, you fire up your engine and you get out of there. No one wastes time with it. You don't even risk it. Even if you're not a sailboat, because water conducts electricity so well, if the lightning strikes there, then the current could travel and still shock you. So all of those are bad locations. All of those are bad locations. So recall, if we know the electric field, we can find the force as follows: F equals QE. That's because the definition of electric field was the amount of force acting on the charge at that location. So if you want to find the force on the charge at that location, get the F by itself. Oh, and we also said electric field is that, or electric field is also KQ over R squared, and you can see that actually generates our very first force equation, Coulomb's law. Right? So, what other questions can we do? We can start to move individual particles around. We're starting, sorry, did I go too fast? You go? You got it? Okay. Harjot, we're actually starting to look at how they build particle accelerators, like the one at UBC. Not like the Large Hadron Collider, that's a circular one. We're actually looking at how they build linear particle accelerators. Okay? Example 4 says, find the acceleration of an electron placed in between metal plates that are separated by 2.5 centimeters and charged to 275 volts. Okay. What does it want me to find? Acceleration. I'm kind of, because we're doing a bunch of stuff on forces, I'm kind of leaning Peter to saying maybe I want to go like this. I could try using d equals vi t plus a half at squared, or vf equals vi plus at, but you know what, I'm kind of, that's, force also has acceleration in it. In fact, I'm kind of thinking to myself, the acceleration is going to be the force divided by the mass of the electron. By the way, look at the picture. What direction will that electron want to accelerate? Up, down, left, or right? Up, towards the positive, away from the negative. Okay, okay. Well, what did we just finish saying an expression for force was between plates? On the previous page. At the bottom of the previous page. The second last thing you wrote down. Really? What did we just say that the force was between parallel plates? QE, or we could even be more specific. We could say, hey, Mr. Dueck, actually it's what? Q times? Well, hey. I have an F here. I guess I could go Q times voltage over distance. Oh, and there's also a mass. I'll put it in the bottom. You could, by the way, have gone dm, but to me that looks like decimeters or decameters, so I always put the m in front of the d. That's just me being really paranoid. Q. Help me out. What's the charge we're talking about here? I'll give you a hint. It's an electron. Elementary charge, which is what?
1.6.
Negative. Oh, no. Force scale, force vector. Don't need to put the sign in. Okay. What's the voltage between these plates? Look at the picture. 275 volts. Mass. It's an electron. I know the mass is 9.11, but I can't remember the 10 to the... Negative what? I know it's really small. 9.11 times 10 to the negative 31. Distance. Don't say 2.5. Please be careful. 0.025. We're going to get a huge acceleration. I get 1.21 times 10 to the 12th. Units, it's an acceleration. Boy, I haven't said that for a while. Units, meters per second squared. Mr. Dueck, yes, Hakeem. Isn't that bigger than the speed of light? I don't know. That's an acceleration. And if it accelerated for an entire second, yes, that electron would be violating the law of the universe and going faster than the speed of light. I don't think it's going to take a full second to go 2.5 centimeters. In fact, I think you could actually calculate t, because you know VI is what? 0. Distance, 2.5. You know A. I bet you'll find the time that it travels at that acceleration is really, really, really small. You could actually calculate, and I think this all would be fair game for me to ask on a test, V final, and you'll find it's below the speed of light, and we're not, you know, causing Albert Einstein to freak. Yes? Am I wrong? Oh, am I wrong? Mr. Dueck forgot brackets. Good gosh, Mr. Dueck. You have to stay after school for an hour. Fine. A bigger, how about 1.93 times 10 to the 15th? Is that better? I knew it was huge. Can't believe I did that. Okay, but again, I think, Claire, giving you this question, say part A, find the acceleration, A, find A, and then part B, I would have no problem saying, hey, maybe find how long it takes to travel a distance or how fast it's traveling. Mr. Dueck, well, what if instead of 2.5 centimeters, what if you made it like 10 centimeters? Wouldn't it be going faster than light then? Well, actually, no, because if you made D bigger, that number underneath would also be bigger. You'd get a smaller acceleration. The universe all takes care of itself. Trust me. Sorry, you're not winning a Nobel Prize. You haven't designed a device that's going to go faster than light. Or as the universe would say, ha ha, right? In a very, very ingenious and famous experiment to measure the charge on an electron, that to find that 1.6 times 10 to the negative 19, because that's a really small number, Millikan used metal parallel plates to hold in place a charged oil droplet. The charged oil droplet had mass. He had carefully, accurately measured the mass. He had it hover in place. That meant he knew Fg, gravity, equals Fe, electric force. Aha, now I have an equation, and maybe I can solve for Q. It's very clever. The oil drop remained in place because the electric force balanced the gravitational force. He set up something like example 5. What are the forces acting on that dot? Get the obvious one. Gravity down. If that dot was negatively charged, which way will it want to move because of the electric force? Up. And if we carefully adjust the voltage, we could probably move it up and dial it and reach a point where Fe equals mg. By the way, part A says, what's the sign of the charge on the oil droplet? What would the charge on that oil droplet have to be for it to want to move up, positive or negative? Negative. Okay, so part A, we can say negative. Part B, here is a balanced force equation. But we could even go further. How do we calculate the force between two parallel plates? I'll give you a hint. I asked you this one a few minutes ago and you sat there and drooled. Although we can also calculate electric field. You know what? It's Q, change in voltage over distance equals mg. And this allowed Millikan to, well, hey, he knew the mass very, very accurately. G, hey, he knew 9.8. He carefully measured the distance. He had a system where he could easily, we've been able to control voltage for about 100 years using circuits very, very accurately. Aha! He could solve for Q, the charge. And then this wasn't one electron. This was a big, massive oil droplet. But who's in chemistry 12? He used Avogadro's number to figure out how many molecules, how many atoms there must be in that oil droplet, and then therefore how many electrons, how many spare electrons there must be. It's very clever. I'll show you a little animation in a few minutes.
It's a good combination of science.
Pardon me?
It's a good combination of all the science.
Oh, and just being really clever. I'll show you actually the full setup in a second. Oh, here we go. A particle of mass, I think, is this the last one? Yes, it is. A particle of mass 2.3 times 10 to negative 14 kilograms and a charge of negative 3 electrons is held suspended between parallel plates. Okay, that means we know that gravity equals electric force. We know that mg equals QE. We know that mg equals Q change in voltage over the distance between them. What's this question asking me to find? Oh, voltage. Okay, let's get the V by itself. How? Oh, and by the way, we're finding the change in voltage. I don't know what the answer is. Let's suppose the answer is 200. This would work, don't write this down, if you had 200 volts and 0 volts, or you could go 400 volts and 200 volts, or you could go 630 volts, 430 volts. All it's saying is, look, the difference between the top and the bottom has to be a difference of 200 volts. It doesn't need, say, the top has to be exactly 200 and the bottom has to be 0. You got some flexibility. That's why voltage is always a change in. Much like time, we get sloppy and we don't write the change in all the time, but it's there, right? Anyways, get the V by itself. How? What will I do with the Q? Divide. What will I do with the D? What will I do with the triangle? It's part of V. Don't say anything. Okay. So the voltage is going to be mgd over Q. Did they give me the math? Yep. .015, 1.5 centimeters, divided by, and they said it was 3 electrons. So 3 times 1.6 times 10 to the negative 19. 3 elementary charges. What's the voltage required to pull this off? Whoop. Brackets, Mr. Dueck. Do you get 7,040 volts? Or am I off? 2.3 times 10 times 9.8 times... Is that right? No, yes? Oh, yeah, okay. So I'll go 7,040. Fair bit of voltage, but we can do that fairly easily. Heck, 20,000 volts isn't hard to put together. What's your homework? You can try number 1. You can try number 2. Number 3. So number 3, this time they're telling you the acceleration, and they're saying, hey, what voltage must be causing that acceleration? So I figure that question is fair game going forwards or backwards, right? 4 is good. 5 is good. What are they asking you to find in number 5? Oh, work. Now here's the nice thing, Curtis. You can use, finally, force times distance because the force is constant. You don't have to go change in potential, change in potential, K, Q1, Q2. You can just say, hey, force times distance. You could go change in potential, the change in potential is QV, Q voltage. That also gets you there. Either of those. Okay. 6 is good. 7. 8 is good. Nine. 10. I may go back and nuke a question or two. Let me just see here. 11 we did in our notes. I'm going to skip that. 1, 2, 3. Okay, let me see here. Nuke number 2. Although you got lots of time, too, to work on this. Got a couple of videos to show you.